Okay, so our next speaker is Stuart Masson from Columbia University, New York, talking on superradiance in ordered atomic arrays.
Yes. Thank you very much for the introduction, and thank you to the organizers for the invitation to come to this wonderful place and present some of our recent results on what we're sort of thinking of as many body quantum optics. So taking a system of sort of light matter interactions, but where I have lots of things interacting with that light, and then collective, sort of emergent collective phenomena should drive my behavior. And in particular, I want to talk about this kind of focusing on this kind of idea of multi-channel dissipation. So I have some complicated many body problem, and I look at how it decays when it can decay in multiple different ways. And I'm hoping that by the end of this, I'll have convinced you that these sort of quantum optics platforms are really interesting. And then in particular, using these sort of ordered atomic arrays is an obvious way forward. And I hope I can do that through the lens of talking about superradiance. Okay, so since this is maybe a little bit of a shift, I thought I'd ease everyone in with probably the easiest slide of the conference. If I take some two-level system, I put it into its excited state, it will relax down to its ground state by a spontaneous emission, okay, by releasing a photon, and that photon will have an exponentially decaying pulse shape. So then the question is, well, what happens if I have, instead of one emitter, n emitters, right? I have some large number of emitters, I put all of them into their excited state. What comes out? And the most naive approach would be, well, it's just this, but sort of n times bigger, right? And that is what people thought until Dickey's paper from the mid-1950s, in which he pointed out that this simplified picture overlooks something really important, which is if I have some set of emitters all radiating, then they radiate into the same field, okay? They radiate into a shared path. So if I think of one atom in its excited state, can decay down to its ground state, emits a photon that travels off to far field. But now if I put a second atom here, when it decays, that photon can travel over here and excite the other atom, okay? I have these flip-flop interactions mediated by photons. And furthermore, if I have two atoms in their excited state and I have some detector in far field that measures a photon, okay, I can't tell which atom that came from because they're emitting into the same field. So we have interference. And what all this means is that this idea, sort of naive picture of each atom kind of being treated independently is, as Dickey says, wrong in principle, and many of the results obtained from it are incorrect. And so Dickey in particular focused on the case of all the emitters being at a point, or as he says in his paper, kind of the dimensions of the ensemble being much, much smaller than a wavelength in every dimension. And when you do that, then you have kind of a symmetry of all of your atoms, all of your emitters have to behave in exactly the same way because they speak to the field in exactly the same way. And that gives you a permutational symmetry, which lets you do sort of calculations exactly for large numbers of atoms. And so if I start from that problem, I'm motivated of I have n atoms all in their excited state and I allow them to decay. Instead of an exponential decay, what you see is this superradiant burst, okay? A short, bright pulse that actually initially rises in intensity instead of falling, okay? And I guess at a conference on driven systems, I should point out that sort of these ideas of Dickey superradiance often show up in different contexts. So you have things sort of like, you do have driven versions of this, but I am specifically talking about this transient phenomena where I have some initially excited state and I just want to know how it decays. Okay? So why does this happen? Well, let's think about this sort of permutational symmetry, right? So I can get this again by everything at a point, or more physically, I couple everything to a single cavity mode. And if every atom couples to the cavity mode in the same way, then you reach this same idea of every atom talks to the field exactly the same. And so if I start in a state that respects that permutational symmetry, then every action onto my state has to also respect that symmetry. So my excited state, how can it decay and respect that symmetry? The only way is if it sort of, it relaxes by a completely equal superposition of every atom having been the one that emitted. So I start from everything excited, okay? I emit a photon, I'm now in a state which has kind of exactly one hole equally spread over every single atom. And in sort of, if I look, this has correlations in it, okay? This is some sort of state, and the correlations look exactly like the phase pattern of this operator. And what that means is that the operator becomes more likely to emit again. Okay, this state emits faster than the previous state. Okay, so another photon is emitted, and now I have a state with exactly two holes equally spread in every possible pair, and that has even more of those same correlations. So the next photon comes out faster and imprints more correlations, the next one comes out faster, and you have this runaway avalanche effect, which only starts to slow down when you sort of start to run out of excited atoms that could have been the one that can be emitting. Okay, and that's what leads to this superradiant burst. Okay, so that's kind of the single mode picture. But what I want to do is take this to somewhere where my decay is multi-channel. Okay, so instead of emitting into one particular mode, okay, I can now radiate into lots of modes. So for example, in free space, okay, my atoms will now radiate in all directions. And if they're not all at a point, they all couple to many modes. And the set of modes that they talk to changes depending on the position of my atoms. Okay, so I break that permutational symmetry. And instead of having that one operator, for n atoms, I now sort of generically will have n channels, okay, n different ways that those atoms can decay, which I find by sort of diagonalizing my system path coupling. Okay, and I can be a bit more explicit in what we're doing here. We use this spin model, okay, where we trace out the electromagnetic field under sort of your usual Markovian approximation. So your atom field interaction is sort of spectrally flat, with this sort of idea of my environment has no memory. We have to assume that there's no sort of retardation in interaction, so light travels essentially instantaneously between sites on the timescales of kind of the interactions. When I do that, I arrive at this sort of very familiar looking master equation where I have sort of my Hamiltonian evolution, and then I have this sort of correlated dissipation. Okay, where I can find my Hamiltonian, I have these sort of the flip-flop interactions I described before, and I have these then dissipative interactions, both of which you can just find by the Green tensor, okay, by how the field propagates between atom I and J tells me how atom I and J interact. And then to get to this picture of having n channels, I take this matrix gamma Aj, and I can diagonalize it, okay, and I find the eigenvectors give me the collective loss operators, and the eigenvalues give the rates at which my channels are sort of likely to be the one that receives the photon. Okay, and so these can vary from being kind of very skewed, sort of one channel having being much more likely than everything else, through to them all being kind of equally likely to act. Okay, and so dealing with this spin model for large numbers of atoms runs into a problem that I guess is very, very familiar to everyone in this audience, which is sort of the problem of many body physics in general, is your Hilbert space scales exponentially. Okay, so when I had everything at a point, I only needed those permutationally symmetric states, which scales linearly in the number of atoms, and I know exactly what's going to happen. If they're all independent, then I am just adding things up. There's no correlations. I don't need to worry about the full density matrix. Again, it's easy. In this intermediate regime, I am still generating correlations between my atoms, okay? But there's not any symmetry, which lets me greatly simplify the problem. Okay? What this means is that in these kind of extended systems, exactly what happens in these kind of Dickey superradiance type problems has been debated since the 1970s, but there's no concrete answers as to what happens, except for the fact that people have already done the experiments. Okay, and again, going back to the 1970s, it's pretty obvious that in these extended systems, okay, in these kind of noisy and complex systems, Dickey superradiance still happens. Okay, because you can witness it in everything from sort of thermal molecules through to these more modern things of kind of quantum dots and complicated things like that. Okay, but the issue here is, as a theorist, I want something simple, right? And all of these problems are extremely complicated because all of these problems, I can't look at these just from collective properties. I have to consider what the individual atoms are doing because there is some inhomogeneity in my system that makes things complicated. Okay? So if you think of these kind of early thermal experiments, I have things like Doppler shifts, right? Each atom is moving at different speeds, and that means it then processes at a slightly different frequency, which is going to dephase Dickey superradiance. Okay? If I then think of something like these quantum dots, well, quantum dots, I can't make quantum dots exact copies of each other, right? There has to be some inherent inhomogeneity just from their fabrication. And then most insidiously of all, those flip-flop interactions that I talked about earlier, okay, those will also induce frequency shifts. The fact that the atoms talk via the field is already putting frequency shifts onto my atoms. And if I have some disordered system, well, each atom sees a different set of atoms around it. So the frequency shift it acquires from those interactions adds an inhomogeneous broadening of its own. Okay? So if I want to be able to study this just from thinking about collective properties, I need something that gets rid of at least the majority of that inhomogeneity. And that is why we have been thinking about doing these with kind of ordered atomic arrays. Okay? What we have here is systems where we have sort of optical tweezers. A few people have already talked about this over this conference. I sort of have focused laser beams, and my atoms want to live at the point of maximum intensity. And so I can have sort of these configurable arrays. And so I sort of can manually load these tweezers and then manually move them around and create ordered structures exactly as I want. And since kind of the major breakthroughs in this in kind of the last 10 years or so, we now have people doing all of these things in labs all around the world. David Weld talked last week about how almost every cold atom lab you speak to now are thinking about or already are building one of these tweezer array platforms in sort of various different atomic species and getting more and more complex as they go. And Columbia is no exception, where Sebastian Will's group has been creating a tweezer array of strontium atoms by using these sort of metasurface devices created by Nemfang Yu's group, which is a passive device that can create these tweezer arrays sort of on a budget. Okay, and I should update this slide because now this is not sort of a coming soon. This is a coming very soon because we now actually have, so these atoms have been trapped in the metasurface. And what's exciting about this platform is it sort of lets you build a sort of quantum material atom by atom. Okay, I can arrange my emitters in such a way to generate the properties that I'm interested in. What I'm interested in is something where, as I say, this sort of inhomogeneity goes away. So if I look now, I have this ordered array. If I think about what my atoms in the center are doing, that kind of inherent inhomogeneity that comes from seeing different neighbors and exchanging photons with a different set of neighbors, the atoms in the middle all see approximately the same set of neighbors, which is going to limit my inhomogeneity and hopefully allow the collective effect to dominate. And so what we can do is we can run some exact calculations. So here I just take a chain of 8 atoms. Here I change the spacing between them. And then I excite all of them and allow them to get decay and look at the light that comes out. So in Dickey's case, okay, everything at a point, I see this large superradiant burst. If I move to a distance that is 1/10 of the resonant wavelength of my transition, I now see something that still looks like a superradiant burst to some extent. Okay, it's still a short, bright pulse that initially rises in intensity, but it's less short and it's less bright. And then if I push to 9/10 of wavelength, now we see something that just looks like monotonic decay. So I just tried to convince you that in these types of systems, the sort of superradiant burst shouldn't be dephased by single atom effects because those should be limited. So what is causing this dephasing? The answer is a competition between the fact that I now emit into multiple channels. Okay? So I described that avalanche process of why this happens, right? That I have some initial fluctuation that then speeds up the next photon, which speeds up the next photon, and so on. When I have multiple decay channels, they all do that same thing. Each of them enhances the rate of the next photon that comes out. But what's important is they enhance the rate of another photon like that one. They don't enhance one another. Okay. So when I go to this picture, I have Dickey superradiant burst, and at a point there was one operator that mattered in this very clean avalanche picture. When I go to 1/10 of the wavelength for 8 atoms, I have something like 2 or 3 of my different decay channels are relevant, sort of likely to act. And so they each have this avalanche effect going on, but there's a finite number of atoms, right? There's a finite amount of snow. So none of those avalanches can get as big because they sort of fight with each other. And that's why you see this reduction. And by the time you get to 9/10 of a wavelength, well, almost all of the operators are pretty much equally likely to act. And the competition between them each trying to sort of be the one that acts means that they actually end up, none of them get started at all. Okay, so we now have this picture that we can think about things from a more sort of collective starting point. So we can start asking questions, right? And I think an obvious one when you think about these ordered arrays is, well, how does the geometry of my ordered array matter, right? How do the different sort of lattice structures, how does the different dimensionalities come into play? Again, I can run things for sort of exact numbers of atoms. This is 16. And you can see that the sort of geometry clearly is really important, right? My 2D array, my 4x4 array, has a much larger superradiant burst than either my 16 atom chain or ring. But the issue is, it comes back to this issue of the sort of exponentially growing Hilbert space. I can do 16 atoms. If someone was really, really good at coding this, maybe they could get up to a 5x5, but 6x6 is probably impossible for anyone. And sort of in 3D, I can't really get started. But I want to look at something where the bulk matters, right? That was the whole motivation for this. and I have a 4x4, there's no bulk. So what we need to do is sort of be a bit smarter. And what we noticed is, well, not only as I increase the distance between my atoms, not only does my superradiant burst get smaller, it also gets earlier and earlier in time. And what that means is the point at which you lose your superradiant burst, it's lost at t = 0, okay? So my minimum condition for a superradiant burst, I'm gonna define as my initial slope being positive. My initial condition is that synchronization, that phase locking process, it has to happen for the first photon, or it will never happen, okay? So I want my first photon to speed up the emission of my second photon. And for someone who does quantum optics, that's just a second order correlation function. Okay, so I calculate the probability, my expectation value of any pair of photons. And then I normalize by the probability of getting 1 squared. And if this is larger than 1, it means the first photon speeds up the second photon. Okay. And my fully excited initial state is easy to actually calculate that analytically. And we find a condition for a superradiant burst is simply the variance of this set has to be larger than 1. Remembering that this set is the eigenvalues of my dissipative interaction matrix. These are the eigenvalues of an n by n matrix. So generically, I have now gone from something exponentially complex to something polynomially complex. In reality, for ordered arrays, these sets, you can use kind of repeated elements in the matrix, and you can actually evaluate this in linear time. And so we can go from being able to do 16 atoms to something like 10 to the 6. At the cost of we're no longer going to be able to generate full dynamics, we're just going to be able to generate this sort of binary piece of information as characterizing my decay as either a superradiant burst or monotonic decay. We can check that this is true. Again, going back to our exact calculations, and you can see on the left-hand side, my condition says there should be no burst, and the time peak emission is at t = 0. So it starts emitting the strongest it will ever emit, and then just decays from there. But the moment my condition goes above 1, the moment this says there should be some sort of superradiant burst and an initial rise in intensity, you see that the time of peak emission does become finite. So what we're going to do is define sort of this point at which my condition says there should be a crossover between those two regimes. And we can calculate what we call the critical distance in different geometries to be able to make these comparisons between how does arranging my atoms impact Dickey superradiance. Okay, so we can also, before we do that, I guess we can quickly look at this expression. And not only is it fast to calculate, but there's also some sort of intuition that you can gain from this expression about why these processes are happening at all. And that's if I look at sort of what I need a variance of a set to be large when I have a fixed mean. Okay, and to get around that, what I need is for this to have large values in it, right? Because I can't have negative decay rates. So if I want my variance of this to be large enough, I need there to be some large values to drive up my variance, which means I need my emission to be sort of sufficiently focused into a small number of channels. Okay, and there's two ways we could do that. One is through destructive interference, by which I mean that out of those channels, there are lots of them that I can't emit into at all. So the decay rates into those channels become 0. And that lets the rest of the set be large enough for the variance to be large. And the other way is sort of more simple, is constructive interference of just some of the rates get really, really big. Okay, and that's enough to drive it. So the question is, which happens in ordered arrays? So I can look at 1D arrays to start with. Okay, and we can find this critical distance, this crossover point between the two behaviors. Okay, and we can see it saturates as I increase the atom number to something, depending on the polarization transition, something around sort of 0.3 of the wavelength. But I can also, because these are ordered systems, I can also go to an infinite picture, decompose everything into block waves, find this, this decay in terms of momenta, and then just integrate it from a Brownian zone. And then I can find that not only does my critical distance saturate, it's saturating to exactly that of what the infinite array would give me. Okay, so this saturation is a true saturation. Okay, so 2D did better. When I did my finite size calculations, it also does much better here, because not only is it can we see superradiance at larger interatomic distances, this actually diverges. Okay, and so again, by doing this infinite treatment, we can find these sort of plateaus should diverge as the square root of the logarithm of the number of atoms, which is a slow divergence, but you get some help from these kind of little jumps, which are geometric resonances where the set of decay rates suddenly changes. Okay, so 2D does better than 1D. So you might not be surprised to find out. Yes.
Can I ask about the biggest? Why is the curve actually not monotone? There seems to be some atom number for which there are two.
Yes.
What is the other?
Okay, so these call them geometric resonances. So if you think as I increase a lattice, if I'm at, okay, so if I have two atoms that talk to each other via a field, there is a way of talking that is just sort of a half oscillation. There is a way of talking that is a full oscillation, and the atoms can't tell the difference, right? But at very, very close distances, that full oscillation doesn't fit. So there is only one way of talking. But as I increase the distance, they suddenly hit a point where essentially an extra diffractive order becomes relevant, okay, where there's extra way of talking. And so the set of decay rates suddenly changes, and you have these sudden changes. So that's what leads then to these kind of discontinuities. So if you look, they're sort of all centered around, like this one's at like half a wavelength, this one's at 1/√2. So it's all just to do with different distances in the square array. Okay, so yeah, in 3D, now not only do we diverge even faster now as a power law in the number of atoms. And here a power law is what we find from doing our infinite treatment, but here we hit those geometric resonances so frequently that actually finding a plateau long enough to fit isn't possible. So we just fitted the whole thing to a power law, and that also seemed to work quite well. And what I like to point out with this plot is, I started this on slide 3 talking about Dickey saying, I want to do something with an ensemble that is much, much smaller than a wavelength in all dimensions. And now we're looking at basically the same physics can arise where the nearest neighbor distance in your system is sort of more than a single wavelength. Okay, so why do all these dimensionalities act so differently? Well, I sort of talked about this as what it could be from destructive or constructive interference. And the reason 1D saturates is because it comes from destructive interference. Okay? In 1D, you see superradiance because lots of the decay rates are 0, and that allows you then to have the rest of them be bright enough. And so then as I add more atoms, once I have enough atoms that the decay rates have gone to 0, adding more atoms makes you infinitesimally darker and doesn't really change anything. But in 2D and 3D, superradiance is occurring at distances where there are no dark rates left anymore. And instead, it has to be driven by these divergent rates. It's driven by constructive interference. So then the more atoms I add, the brighter and brighter those brightest channels get. Okay, so what we talked about so far has all been very much sort of in theory land. I'm talking about kind of infinite arrays of 2-level atoms where I'm collecting light in 4 pi, and none of that is experimentally feasible. So let's now think about how would we do an experiment looking at this kind of controlling the pulse of light that comes out by changing geometries. And what we were proposing is to do this with alkaline earth atoms. Okay. So alkaline earth or alkaline earth-like atoms are species with 2 sort of relevant electrons, which means they have a slightly richer spectra than your sort of normal alkali atoms. And what's important here is that it gives you this structure where you have these metastable 3p states, so the 3p2 and 3p0 are metastable. And you have these excited 3D states where this decay from up here is at infrared wavelengths. Okay? So in all of these plots where I'm saying I need my distance to be small enough, it's in units of the wavelength. So a trick you could do is you trap at optical wavelengths, and then you do the science on a much longer wavelength. Okay? So in ytterbium, these transitions actually turn out to be at telecom wavelengths, which is nice not only because it gives us that trick, but also because doing an experiment, sort of collecting the light and dealing with the light is all very easy. These components are already well available. And the other species we're going to consider is strontium, where these transitions range from about 2 microns to 3 microns. Okay. And one detail is that obviously this is not a clean 2-level system anymore. There are simplifications that can be made, which if anyone cares, I can tell you about later, but I'm going to skip to the results where I've made those simplifications. And we can show here if this is a 12 by 12 array of ytterbium emitted to a particular state. We're collecting light now on a particular transition that's emitted in a particular direction. Okay? And you can see this clear non-monotonic behavior in the decay. And then I increase the distance and it goes away. And then I increase the distance again, and it comes back. Okay. And this kind of highlights that this is not a particularly trivial problem, right? Things show up that you potentially wouldn't be able to predict unless you can calculate these sorts of correlation functions like I was doing earlier. Okay, so this is now a conditioned version of what I described earlier, where I'm conditioning that I care about the slope of the light emitted on a particular direction, on a particular transition in a particular direction. Okay, and I can calculate this thing, and where this red line is above this dashed line is where I expect to see a superradiant burst. Okay, so instead of calculating lots and lots of these curves, I can instead just make this, which takes a few minutes, find the 3 points to make my fun reveal for my talk, and sort of save lots of my own time. But what's much more valuable than my time is that of kind of experimentalists. And so we can also use these same ideas to help guide people who want to do experiments on sort of many body decay in these systems. Okay, we can point out, where do you need to put your detector, what transition you should be working on, and all of those kinds of things. And maybe the experiment you're interested in doing is just making the largest superradiant burst you can. And then the best way to do that is you find the longest possible transition, which is in strontium, this 3D3 to 3P2. We're now thinking about a sort of a distance relevant to optical lattices. And you can find this two-level system where you can then see this sort of large superradiant burst. And you can calculate as a function of atom number that this scales sort of faster than linear in the number of atoms, which is sort of the hallmark of superradiance. Another thing that shows up out of this is we can sort of, all of these plots I've been showing have been where my excited state can decay to multiple places. And if you think of a single atom and it can decay sort of on 3 different transitions, the weighting of those transitions is given to you by atomic physics. Okay? It's given to you by dipole matrix elements, by Clebsch-Gordon coefficients, right? And it's not something you can particularly play with. But when I have these collective systems, as I increase my number of atoms, okay, these dashed lines are this single atom limit. As I increase the number of atoms, I see more and more of my light is emitted onto whatever the brightest of those transitions was. Okay? And this comes back to this idea of this is an avalanche process. Okay? And so if I can decay to multiple places, whichever one gets started first, then it speeds up and up and up. Okay? And it steals light from the other transitions. Okay? And the more atoms I add, the bigger that enhancement is and the more it can steal. Okay? And again, we can look at the patterns in our superradiance condition and match them to the pattern here. And so if you want to do an experiment where you want to see these effects, we can show you places you should work. And if you want to sort of get rid of these effects, we can also point out where these effects are minimized. Okay, and so this all comes back to sort of ideas of when I have these multiple channels and I have sort of these interaction between avalanches, but somewhere that's much easier to look at those kind of competitions is in waveguide QED. Okay? So now I have some sort of periodic array of emitters coupled to a 1D channel. Okay, and my 1D channel now has 2 modes, right? It has propagating left and it has propagating right. I can also have some parasitic decay. Okay, so this can be decay into free space or sort of decay via phonons and things like that. And so I can now look at this system, which is much simpler, and I can see again superradiant bursts can be observed. And so here we have sort of both a bidirectional waveguide, which is where this gamma L and gamma R are the same, and in a chiral waveguide, where one of these is sort of biased to be more likely. Okay, we can also come up with the same sorts of superradiance conditions. So these numbers on the top are relevant to experiments with superconducting qubits coupled to transmission lines. And there you can see you only need something on the order of sort of 5 or 6 superconducting qubits, and you'd be able to start looking at this sort of physics. The numbers on the bottom are relevant to experiments with sort of cold atoms coupled to nanofibers. And there you need a lot more atoms, but still something on the order of sort of 50 to 100 should be enough to start probing this physics. And we can also look at disordered arrays. And again, you can just see sort of essentially the higher my optical depth, so the higher, the more of my light that is usually radiated into my 1D bath, the fewer atoms I need to be able to see all this physics. What the waveguide gives us that's nice, which you don't get in free space, is I have very controlled outputs, right? I have something that is guiding my light and taking my light to certain places. So then I can look at, well, if I have my initially excited ensemble, okay, at the end of my experiment, my transient pulse has been emitted, all of my emitters are in their ground state, and I now have some packet of photons that's going to the left and some packet of photons that's going to the right. And so you might sort of think, well, that would just be sort of binomial statistics, right? On well, how much goes left and how much goes right. And that's true when you're in what we call the mirror configuration, which is where the atoms are spaced such that they actually only speak to one of the modes, so one superposition of the modes. So this kind of goes back to being the original Dickey superradiance. And there, the action of the sort of the back action of emitting a photon left and right is exactly the same. So then they do enhance each other. And you then do just have a coin toss, and you sort of see the bidirectional case, you have a binomial centered on no imbalance. And in the chiral case, you have sort of a binomial that's now shifted with a peak that makes sense when you look at just the single atom rates. But if I move to some distance where I don't have this kind of condition, right? So now I'm moving somewhere where my left and right operators are different. Then instead of seeing something binomial, you see something that approaches being perfectly flat, okay? So when you think of your binomial distribution, right, you can think of sort of Pascal's triangle and the numbers get big in the middle and sort of small on the outside. Well, when I add in my avalanche effects, when I add in this sort of enhancement that comes from emitting photons of the same type, it essentially perfectly cancels out that difference in your Pascal's triangle. And so you get something which is approximately perfectly flat in this bidirectional case. And then when I introduce my chirality, I introduce some preference into going in one direction, I now see something that's very heavily skewed to that direction. So I have a much, much higher likelihood of all my photons going in that one direction than the other one, okay? So this connects back to these ideas of sort of overcoming Clebsch-Gordon coefficients with collective effects. Here I can now sort of enhance chirality with my collective effect. Okay, and so these kind of huge shot-to-shot fluctuations are not just, don't just appear in the waveguide, but sort of generically appear in superradiance problems in general. And so when you think back to sort of my thing in free space, that will have these same shot-to-shot fluctuations, both in terms of how much light is emitted on each transition, and also in the directionality of the pulses that come out. Okay, but a simpler system of sort of atoms scattering in free space are these ideas of superradiant scattering in BC problems. So this was first done in the late 90s by Wolfgang Katterle's group. You take a cigar-shaped BC, you shine in a beam perpendicular to your cigar. Your cigar wants to emit out of the so-called end fire modes. Okay? It wants to emit out of the ends, which gives you two dominant modes in the scattering. And the result of sort of this scattering is then sort of atoms with momentum being created in your condensate, and the creation of those atoms with momentum can essentially just be mapped back to a Dickey superradiance problem. And so what this experiment's looking at is doing the same thing, but instead of the sodium BC, the Wolfgang Katterle did it with, doing it with an erbium BC. Okay, so erbium is one of these sort of magnetic atoms. Okay, which means that it has direct interactions. And those direct interactions depend on the direction of your magnetic field, okay? So if my magnetic field, depending on how it's aligned with my condensate, I have for my two scattering modes going this way and this way. And so if one of them is aligned with the magnetic field and the other one is perpendicular to the magnetic field, the creation of phonons in those two directions has to be different because the dispersion relation of phonons in those two directions is different, okay? And I can break the symmetry of emitting out the left end and the right end, okay, so sort of just like in the waveguide case, and then I can measure the blobs of atoms that are created, and you can see that we think that there is some sort of role in the results here where this, the fluctuations that they've observed in the experiment are much, much larger than what you could expect from sort of a coin toss model without this avalanche effect being put in, or from kind of the experimental noise in that system. And so with my last 1 minute, I would take a slightly different tack, which is to quickly sort of advertise another experiment that we've been involved in, which is with the group of Dan Stamper-Kern, where they're now introducing these ideas of tweezer arrays into a cavity QED platform. Okay, so if you think of your standing wave of a cavity, you have sort of essentially a G naught, right? So the coupling strength between your emitter and cavity mode multiplied by a cosine, okay, which means that you have points where you couple to the cavity mode with a positive phase and a negative phase. And then you can show if you couple them all with a positive phase, then the light that's scattered into the cavity in these kind of Rayleigh scattering experiments scales close to n squared. But if I put them in such a thing that they're destructively interfering, so I alternate by talking positively and negatively to my cavity mode, then instead we see this sort of strange stepped behavior where when I have an even number, I can, in theory, perfectly cancel everything out. And in the odd case, I can't. And so given that I've been buzzed, I should just quickly thank all of the people involved in kind of the various projects that I've talked about. If these are the references, if anyone's interested, and then I will hand back to the chair.
Thank you. Thank you for this very nice talk. Questions?
Thank you. So are the photons correlated when the ones that are coming out of this waveguide, are they entangled?
Yeah, so that's a really good question. And it's a difficult question to answer, but it's one we actually are looking at. So what you can do is use the Alkaline-earths theorem, which basically what you do is you can look at the sort of temporal profile of the pulse that comes out, and you can find a set of orthogonal temporal modes to describe that. And so this is based on work by Klaus Molnar and his group. And so they work in a perfectly chiral waveguide, so there's just one pulse coming out, and you can then decompose it into these things, and you show that the light that comes out in a superradiant burst, it's not a Fock state, but it has very high overlap with a Fock state. So I think they have in their paper something like a plot of 60 atoms, and 54 of the photons are in one temporal mode. So it's not a Fock state, but it is kind of close to a Fock state. And there's also work by Stuart and his group, where they show that even though it's not actually a Fock state, it still maintains a lot of the metrological properties of a Fock state. So it certainly is entangled coming out, and potentially in a useful way.
And the one that's balanced going left and right, do you get number squeezing between the left and right traveling numbers?
That's a good question. And yeah, so that's, I guess, I say we're sort of trying to work to generalize these ideas to where I can look at this sort of spatial and temporal character. And that's a very good question that hopefully I could give you an answer to in a month or two when we get back, and the graduate students been working on this. So.
So regarding this dipolar BEC experiment, so this is a fairly dilute gas, right? So this is a fairly dilute gas, and also there is no ordering in some sense. So on an average, you don't have many pairs of sort of sub-wavelength emitters or even something close. So is there some clarity on how this is happening, that you're sort of getting these, what would be something related to collective effects in this?
Okay, yeah, that's a good question. So I can give you my toy model theorist approach to why I think this works, which is if I have my BEC, I think of a perfect BEC at equals 0. Every atom, okay, the density might have, you can get from the density some average distance between them. And as you say, it's dilute. But each of those atoms has a macroscopic wave function, right? And they all have the same macroscopic wave function. So they all still couple to the field in exactly the same way. So that's, you can sort of argue these indistinguishability type things by essentially taking a single mode approximation to your BEC, where the spatial structure of your BEC decouples from the momentum part.
So you showed some results for, I think, a 12 by 12 array, and you used a cumulant expansion. I was just curious, how reliable is that approach? Are there limitations? Yeah. What's the way I should think about that? Yeah.
It's another great question. So one of the hard things of doing any numerical methods for the system is we don't really have a way of benchmarking anything. So with the cumulant expansion, we are able to benchmark things for small numbers of atoms, where what we generically find is when the distance between atoms is reasonably large, it works fine. The smaller the distance gets, the worse it gets, which is perhaps unexpected. But yeah, you're right. If we try to work in a regime where we think we're fine, but ultimately, I guess there's not any experimentalists here for me to try and sell this on, but ultimately the best way to look at this is actually doing these experiments and where, you can, it's like a quantum simulator of itself, right? That can then get around this. I think that's ultimately what we are trying to push towards, I guess, with all of slides, but all of these ideas is trying to set out a roadmap of this is something that's feasible with current technologies and that people can sort of be working towards. And I think we're much more confident with the things from the G2. So we're very comfortable to say there definitely is this initial rise in intensity in these regimes. With the cumulant expansion, where we're sort of, maybe that's overestimating, maybe it's underestimating how big the signal you would actually be able to measure is.
Have you tried things like a discrete truncated Wigner? Is that a good approach here, or is that?
We haven't, but there was a paper on the archive a month or so ago from Michael Fleischhauer, where they did take that approach. And I think they seem to find similar things, which is that when the correlations aren't, when the distances are larger and the correlations are weaker, it works better. But again, I think there is a plot in that paper that compares the truncated Wigner with this cumulant expansion. Because yeah, there's a few other groups that have also been using these kind of cumulant expansion. We're not the first people to start using this technique. So borrowed it from various other people. So yeah, there's certainly, I think one of the things that's probably true in these systems is, whilst it's this exponential Hilbert space, it probably doesn't visit all of it. So there probably is some clever way of truncating my Hilbert space in a way where I capture everything really well. And I'm not best placed to work out what those methods are. So if that's something anyone has any ideas on, I'd be happy to hear.
Okay, so I think if anyone has more questions, we can carry to the coffee break. So let's thank Stuart again and both our speakers actually, and this ends it.